Just like StripMap app, the workflow is broken down into a number of steps. Yesterday, you went through each step in detail. Here, what I've done is I've grouped the steps together into bunch so that we run a bunch of steps in one go, and then we go talk about what is happening in each step. What was the question? You don't need to have reference and secondary in separate XML files. You can have them in topsApp.xml, and that will totally work as well. However, if you are processing multiple interferograms using the same imagery, this reference and secondary file mechanism just allows you to reuse the XML without having to recreate everything all over again in different topsApp XML files. So for the directory setup, like I said, we've already included the XML files in your support docs folder. You just run this script, and it should fetch the XML for you. These XML files are structured like we've shown above. And in the later part of the notebook, I have a bunch of user exercises that users can then play with these XML files to turn on, turn off options and rerun the workflows. So once you've copied the XML files, just make sure you are in the InSAR folder. I have also, just to be safe, added the change directory to the InSAR folder before every step. Because I often just tend to open up random notebook cells, do some debugging, and close it. But just to make sure that you run the topsApp command when you're in the inserter folder, from the inserter folder. So the first thing we're going to do is we're going to get a quick overview of our interferograms. So this is essentially 3 different processes: startup, pre-process, and compute baseline. Yesterday, you saw execution of single steps. Here, I'm starting at one step and ending at another step. So these 3 steps will be run one after another. And go ahead and push that button. It's probably take a few seconds to run. The step startup is very simple. It just sets up the folders that it needs to preserve state between running different steps. Pre-process is where it actually reads your reference and secondary files. It looks at your region of interest and says, oh, you only asked for SWOT 3, you only asked for this region of interest, I'm only going to use these bursts. And if you look at the screen output, that should reflect it. So it said it found 9 bursts in SWOT 3 because you only asked for SWOT 3, but you asked for region of interest. So it says, oh, only 4 bursts are of interest. So it's only using the 4 bursts for processing. And once that does that, it computes the baselines in the 3rd step, and it basically gives you the perpendicular baseline. These are just reporting numbers. These are not used for processing. This is just user convenience. Once you run the step, you can look at the ls pickle step. For every step you run, you will see 2 files that will get generated, one with the step name itself and one with the step name.xml. And these are the files that tell ICE what steps have been run so far. And if it needs to save some temporary variables, these are those get stored in these pickle files. This notebook was initially developed by David. He did a nice thing of putting in potential errors you would encounter at different stages. Suppose you gave it multiple save files to stitch, but actually there is a gap between the 2 save files so that you cannot contiguously put them together. That's one error that'll show up. Another thing that happened a lot early in the mission is you may have one SLC in one version and the next SLC in the track in another version. We explicitly prevent them from being stitched because there's no way of guaranteeing that that would work. So I'm seeing people getting questions about where the XML files are. If you'd run this step, it would have copied the XML files for you. Then please check the folder from which you're running it. You're probably running it from the wrong folder. You probably skipped certain steps in between. All right. So what happens when the data is unpacked? The data is unpacked into its own folders called reference or secondary that you specified in your reference XML or secondary.xml. And the structure of this folder is it has a iw3.xml and a folder called iw3 with each burst in it. So like we saw the screen, 4 bursts were unpacked. This iw3.xml contains all the metadata, all the radar data, orbits, starting ranges, etc., that you need for processing. And these are actual imagery. In this case, to save disk space, we generate this as VRTs. So none of the data is actually pulled out of the zip file. They just point to data within the zip file that GDAL understands. And these are virtual files. You will learn more about you probably learned about this already in the GDAL tutorial, and you'll probably learn more about it in the GDAL exercises. Once you have a good overview of your interferogram, the next step is to get the DEM. The DEM you can get by running the step verify DEM. Make sure you have your .NET RC file set. So in my case, I'd already downloaded the DEM, so it should just say everything seems fine, it's been verified, and we're good. Otherwise, you should see it downloading the DEM for you over the area. And again, there are multiple possible issues that you could have encountered. One issue is you did not set up your netrc file. Another issue is you probably have a special character in your password, in which case you have to escape it with a backslash in your netrc file. And the third site is this. The third one happens rarely, but it does happen that the DEM FTP site is down. If you are having trouble with DEM, we also have a copy of the DEM that you can just copy from the bucket to proceed to the next step. If you copy the DEM, just make sure you run the verify DEM step again, and there are no errors when you run that particular step. If you just identify the DEM and say, okay, you're good to go. Let's hit this button because this is probably like yesterday. This is the longest running step, topo. So go ahead and push the button on this. And this does exactly the same thing that Harish spoke about yesterday, but now this will do it burst by burst. So you will see the same process being applied for each of the individual tiny image bits. This should take about 20 minutes for people to run. I've already run it, so I'm just going to talk about the outputs while you guys are running it. Anyone having trouble? Did people manage to get the step started?
Some people are having trouble with XML files earlier back in the chat stream. I don't know if that's been resolved or not, but since you have 20 minutes to wait, you might try to address some of those. I don't know.
Yeah, I don't see. I don't see an actionable error message.
Well, maybe the person having the trouble is Veronica. It looks like she's having a problem. Maybe she can describe it a little bit for you. Several people are working on it, so maybe it can be worked offline. You can just continue.
Did anybody manage to get the XML files automatically from the repo? Or is everyone having trouble with this?
It's working fine for me. I think most people.
Ah. Yeah, just to remind people, if they don't know where the notebooks are, this particular notebook will recreate the environment and everything. And these IS2 docs is just a Git repo. If you do a Git pull, if you deleted anything in it, you should be able to get it back.
Yeah, and whereas StripMap app created a work directory at the top level, all of these directories, the data and InSAR directory, are right here in at the notebook level. Right? So people might have a hard time finding if they look at the top level.
Make sure you're running the 2020 notebook over the other.
Ah, that's true.
That's
The 2019 notebook does not have any of the bucket backup stuff. And it's a different data set.
Other than that, it should be fine.
Yeah. So when topo runs, you will essentially see this as an output when you list the output once you're done running. Just like you saw JOM reference yesterday, there's a folder called JOM reference here. And again, the data is organized by SWATs. And within each of these SWAT folders, data is organized by the burst numbers. Same outputs, a file for pixel by pixel latitude, a file for pixel by pixel longitude, a file for pixel pixel height, and the line of sight. So we're essentially replicating the same process we did in StripMap, but we're doing it burst by burst. And all of these come with VRTs. You should just be able to run gral.info.vrt, and it should list min, max, and the valid numbers in each band. And these are just useful diagnostics to have to look at the data. If you want to plot the outputs of any one burst, here I'm plotting height, the line of sight first band, and line of sight second band. This is what it looks like. For that burst, height varies from 1,300 meters to anywhere 2,700 meters. So it's some rough terrain in Nevada that we're looking at. The incidence angle is a slowly varying field. You see it changes from about 41 degrees to about 47 degrees within SWAT 3. And the azimuth angle also is a slowly varying field. It only changes about less than a degree over the burst. So these provide the line of sight vector information to transform, to bring in interferogram unwrapped phase into your modeling space. So far, we're essentially doing the same thing we did with StripMap app. We've done topo. The one slightly different thing we do in TOPS from StripMap is called enhanced spectral diversity. If you, in the table of contents, if you took out enhanced spectral diversity, the workflow is essentially the same as StripMap app, except you're doing it over tiny bits and there's a mosaicing. Everything else is pretty much the same. So what is enhanced spectral diversity? We already spoke about how Sentinel-1 collects images in bursts. So this is how the bursts would look like between the reference and the secondary image, for example. And these bursts have an overlap in the azimuth, in the along track direction. So if the burst is typically about 1,500 lines, there's typically about 100 lines of overlap between one burst and the next burst. So why is this important? Like you said,
there are some questions about the plots before you go far ahead.
Happy to answer. Yes.
So can people who are having problems explain what the problem they're having is?
Yeah, how is it different? Are you seeing a flat line for topography? How different does it look? Like, what do you mean by different? So John and Lauren.
Flat line.
That basically means your NetRC is not set up right, and you probably have a 0 DEM because it could not successfully download a DEM. So if you go back to the verified DEM output, you should probably see something that raised a flag. Yeah, so whoever is not seeing any topography in this height plot have not set up their NetRC files right. They've not managed to download the DEM correctly. So you should have seen error messages when you ran the verify DEM step up above. You should have seen some errors getting flagged in the step or in this.
You can run the workaround part, right? There is that.
Yes, you can delete these demlat files in your folder and copy it from the bucket. That is just an informational. It's not a warning. It's an information saying the parsers themselves have a lot of ways of control, and if you don't specify it, it uses whatever it reads from the TIFF file. So that's totally fine. Yes, the error that you're seeing means you did not set up your .NET-RC file correctly, or you did not set it up at all. So if you don't have the DEM download working right, you can pull it from the bucket following this after deleting these files from their local folder. The instructions are also provided in the notebook on how to set up your NetRC file. I would suggest you find that. We've included the link here, and it should also be on the Slack and in emails. All right, moving on to the ESD part. Like we said, the antenna scans as it flies. As a result, you need to very precisely know the center of the antenna scan location in time to the precision of few microseconds. However, this is very hard to achieve in reality. So what we do is we actually look at the data and estimate the correction in time needed to get this antenna rotation center correctly. So if you create an interferogram with a burst and another interferogram with the burst next to it and look at the overlap region, you should see processing artifacts if you don't have the correct antenna rotation center in your information. So what we are doing in this process here, we are estimating.
Someone's typing really loudly.
Me again. My bad.
So this ESD process essentially estimates that antenna timing correction of one image with respect to another image. There is no way of estimating it absolutely correctly, perfectly for any image by itself. But TOPS allows us to estimate the error in one image with respect to another. Remember, InSAR is a differential measurement. If you make the same error in both images, they cancel out. So you're essentially trying to minimize the error. And by looking at the overlap regions, the top interferogram and the bottom interferogram should show you the same phase. If the phase is different, then you made a processing error. And that's the correction factor that gets estimated here. And to do this estimation, we don't have to process this whole large volumes of imagery. We only are interested in the overlap between bursts. So the first thing we do is we do the subset overlaps. We only extract out the 100 lines out of the 1500 lines corresponding to the overlap region. Then we resample the secondary image bursts to the reference image only over these overlap regions. So you're doing only 10% of the computation instead of doing the entire bursts. So you again, once you've estimated the offsets for this overlap region, you resample the secondary image, you create the overlap interferogram, then you do the cross multiplication between the top overlap and the bottom overlap, and then we estimate the azimuth offsets. So if you've already run the topo, just push the next set of steps, which is we start at subset overlaps and end at ESD. This is a fairly less computationally intensive, like I said, because we're only doing about 1/10 of a burst. So it runs really quickly. Just to illustrate, here is burst 1 and here's burst 2. And just to convince yourself that there is a small overlap, we've pulled out the overlap regions between the two images. And you see these features line up. So the bottom of burst 1 lines up with bottom of burst 2. And the phase, of course, is random because we're looking at SLCs here. So this overlap is what we exploit. Coarse offsets is same as what we did yesterday in StripMap app. It's just using the geometry again to take the lathlon from the reference image, finding where it shows up in the secondary image. And another thing to notice here is Sentinel-1 flies a very tight orbit tube. So if you look at the azimuth offsets, because of the way they image, the variation in azimuth offset is well below a single pixel. So it's almost a constant for a given slant range. And this is very absolutely needed to make TOPS interferometry to work. This is if you were to do the same with ALOS or other sensors, you would see a lot more variation in the imagery in the azimuth offsets. Again, with the range offsets, the variation is well below a pixel. This indicates that they're really able to control the orbits really well on the Sentinel-1. So once we have these offsets, you only create the resample part in the overlap regions. And in the overlap regions, we adopt this nomenclature where we say bottom 0102 implies from the bottom burst of the overlap between burst 1 and burst 2. Top implies from the top burst of overlap, 01 and 02. So you create a bottom interferogram for the overlap. You create a top interferogram for the overlap by just cross multiplication. If you created these interferograms, you would, I'm just showing the top interferograms here. Any guesses on where the earthquake shows up? So this plot is the overlap between burst 1 and 2, overlap between burst 2 and 3, overlap between burst 3 and 4, the center burst, that's right. So this is only the top part of the overlap. The bottom part will also look very similar. So when you do the top and the bottom cross conjugate, you should end up with fairly constant phase, or zero phase everything is done right. At the end of running ESD, you will get the coherence for all these top-bottom cross-multiplied interferograms. You will also get the phase difference between the top and the bottom. You see it's constant. So we saw the top interferogram had this pattern. The bottom interferogram will also have a very similar pattern. And when you do a top-bottom cross-conjugate, they cancel out. But again, you see a slight hint of being some phase being slightly off here compared to the green background. That's likely where deformation occurred, but it's not large enough to show up to impact the azimuth on the top cross interferograms in this case. So once we've done this phase, we can easily make a histogram of it. You see when you do a histogram, it's slightly off-centered from 0, but not by a lot. So we're very close to having really good azimuth co-registration out of the box with Sentinel-1 data for this particular pair. If you are seeing SLC backup directory, you're probably running a 2019 notebook. I would strongly urge you to use a 2020 notebook. The middle overlap plot in the notebook. So these are chronologically ordered: 01, 02 overlap, 0203 overlap, and 0304. It's what is printed in the string that shows up on your screen. That's okay. If it's not in that order, that's totally fine. That's because I'm just using wildcards here. Yours may have pulled in the file in a different order. Whatever shows up here is in the order of the string. All right, and this is what you typically see with Sentinel-1 data. The offsets are small, but they can be big. It depends on how well they're tracking the orbits and their clocks. Those can drift. They typically, you can see offsets of up to a microsecond sometimes. So that is in the azimuth direction. Another thing that we do differently compared to, say, GMT-SAR is the range co-registration. Why do we do this? I would say if you've gotten this far, push the button on the range co-registration as well. This would use traditional amplitude correlation to estimate a constant range offset between the two scenes. Note that when we described the RDR to GEO and the GEO to RDR process yesterday, we are purely drawing rays from the satellite to the target and back to the satellite. But we know in real life, all these rays pass through the atmosphere, and the atmosphere on one day is different from the atmosphere on the other day. On the order, this difference can be on the order of tens of centimeters in the worst case. Very often it's not that big. but this can be big on the order of tens of centimeters. So what we're trying to do in this range co-registration step is we're trying to correct for this differential bulk delay through the atmosphere. This correction, 10 centimeter difference, Sentinel-1 has a pixel spacing of 2.5 meters. 10 centimeters has very little impact. It's about 5% of a pixel. When it hits 20 centimeters, it's 10% of a pixel. This, when you typically do an analysis for a wide area tectonic analysis, you end up multi-looking a lot, you end up filtering your interferograms. You don't see this impact at all. However, if you want to do something at full resolution, if you remember Paul's slides yesterday, if you misco-register the images, the amount of misregistration impacts your coherence and the quality of your phase information. This range co-registration, you can skip for if you're doing wide area multi-look stuff. But if you want to do things at high resolution, this has a fairly noticeable impact. But we do this by default, since we're only doing this again on the overlap regions. We're not doing this over the entire bursts. It's a fairly small amount of data. This runs very fast, so we just put it in as a default. There are also flags in the XML file to not do this. You can completely turn off ESD, and then you would get GMP-SAR-like behavior, where you don't do any azimuth correction, you don't do any range correction. It just depends on your application. If you're happy with slight phase discontinuities on burst boundaries, you don't need to do ESD for your analysis. But the default is to do ESD and the range co-registration in ICE. So once you run this, this just produces another JPEG file for range misregistration. This looks very similar to your azimuth misregistration plot. Again, you see that the range, there's a misregistration of about 0.07 pixels in range. So that represents the bulk delay, propagation delay through the electronics and the atmosphere between the two images. So we've estimated the fine azimuth correction with ESD by looking at the overlap interferogram and the range offset using amplitude cross correlation. Any questions so far? I actually suggest if you want to take a break, we take a 5-minute break now, and then we can come back to the rest of the workflow. This will also let us answer some of the user questions that may be popping up, and users can wait for their steps to complete. Does that sound good?
Yep.
All right. So yeah, I'm still online. We'll just take a 5 to 10 minute short break to let people processing catch up and to answer some user questions. Why do some lines say bad match? Good question. So when, let's scroll back up. Let's scroll back up to the part where we pulled up burst 1 and burst 2 for display. Before this, when we were showing the overlaps, where did that go? Yeah. So if you see, every burst has a 0 padded area around it. This is the way Sentinel-1 distributes data. The amount of 0 padding is different for each burst. So what most processing software do, including ICE, GMP-SAR, Snap, is we know the bursts are the same size. Easier bookkeeping rather than bookkeeping a size for each burst. So if it tries to run amplitude correlation with zeros in the chip. There's no information in it. So that typically results in a bad match. And when you run amplitude correlation, it's first walking down the line this way, and it's probably pulling 0 chips in and saying there's nothing to do. That's the error message you see in the range co-registration. How would you evaluate when to apply ESD and correg? I think Harish can answer this better since he's seen a lot more Sentinel-1 data. My going-in point is I always do it. There is no way of knowing a priori which images are impacted and which images are not. So I always turn it on. I always run it with it. In terms of how spatially wide so that atmosphere delay matters, anything more than like 20, 30 kilometers in area, I think you'd have to start worrying a little bit. But if you're looking at a tiny area, the atmosphere delay itself would have introduced a bulk shift. So if you're doing a tiny area, you're typically doing high resolution. So you typically always want to do range co-registration on. Does that answer that question? We can apply ESD when the surface moves significantly between the acquisitions, say like hundreds of meters. Yes, so that's one thing. If you do find time, go back to the data set we used last year, which was the Kurdistan earthquake. I'll bring this up as a student question later on as well. You don't see the impact of the earthquake in the differential interferograms between the top and the bottom bursts. Any guesses as to why this is happening in this case? That's because for this particular earthquake, it is oriented in a way such that the azimuth component of the deformation is very small. Most of the deformation is in the slant range direction. If the deformation is in the slant range direction, it shows up in a very similar way in the top interferogram as well as the bottom interferogram, so they cancel out. If the deformation has a long track or an azimuth component, because of the antenna scan pattern, it shows up, projects slightly different in the top burst than in the bottom burst. So any deformation pattern that has a significant along track or azimuth component, you will actually start seeing in the differential interferograms used for ESD. So if you looked at the data set we used for last year, which was the Kurdistan earthquake, and if you looked at this particular sort of histogram for that, you would end up with a double bump, where the main bump was the timing offset. And the second bump in the histogram was artificially induced, well, not artificially induced, was a artifact due to the large deformation in the along track direction of the earthquake itself. So yes, if the deformation is very large, especially in the along track direction, it will impact ESD. If it's hundreds of meters, first of all, co-registration itself is a challenge because you're not matching the right pixel to right pixel using just geometry. So that would be more like what you would do on ice sheets. You would have to do special processing. You'd have to do rubber sheeting, which is available in the strip map workflow as an option, but it's harder to implement for the tops because you have to align each of these individual images in a consistent way, and that's a lot more bookkeeping. So that's not available in topsApp, but it's available in strip map app. can you run a single subswath in strip map mode? You cannot, because like I said, each swath itself is made up of multiple bursts. The equivalent unit to strip map app in TOPS is one burst and not one swath. Can you pull in the data from the S3 bucket? It might be faster than the download. If you're still struggling to download the data, if you run the part that pulls in the data from the S3 bucket. Yeah, so the Sentinel-1 XML files themselves have orbit information in them. Starting sometime in 2018 or early 2019, the information that shows up in the XML file seems to be comparable quality to the orbit files, but before that, definitely not. I would always recommend pulling in an orbit file because there's quite a bit of variability in the quality of orbits that are included in the annotation file itself. The quality of the orbits in the annotation file will let you do stuff to meter scale geocoding accuracy, whereas you really need the high quality orbits for geodesy and interferometry. All right, looks like we just spoke through the entire break. I hope people got some time to stretch their legs. Do we just want to resume? Or should we give people a couple more minutes? All right, so let's resume. So you haven't already pushed the button on this cell. So in the previous step, we've determined the offsets we need in range and azimuth. Now we are going to use those offsets. This is exactly StripMap app to create the co-registered bursts. We do fine offsets, which is geo to RDR that we saw yesterday in StripMap app, and then fine resamp. In this case, the difference between coarse resamp and fine resamp is we resample the entire bursts now because we're now ready to generate on the interferogram. We were only doing coarse resamp to estimate the differential corrections, and we had optimized it by doing only the overlaps. So, and the fine offsets will again produce files that will have a similar structure, one azimuth offset file per burst, one range offset file per burst. And fine resample will produce a correg SLC directory with exactly similar structure, a folder for swath, and individual files for burst. You will see that there are essentially two time-consuming processing steps: topo or RDR to geo, and geo to RDR. Topo is the slowest step. Geo to RDR is slow, but It's a lot faster than topo. The RDR to geo or topo essentially is the slowest step because our radar image is a 2D image, whereas the real world scene that we're imaging is a 3D scene. So you're using the DEM and searching the scene to find a projection that matches our 2D image. So you're searching in 3D space for a 2D point. So you have one extra dimension to search through. That's why it's slow. Whereas the other direction, if you know a lat-long height, and you want to know where that lat-long height shows up in your radar image, you're going for 3 dimensions to a 2-dimension image. So you're reducing the dimensionality. So it's a faster operation. So that's why you'll see the rest of the processing workflow go through really quickly, and the slowest step being identifying the right point in the DEM that matches your radar pixel, which happens in topo or RDR to geo. So once we've run through the co-registered burst step, we now have the reference bursts, and we have the equivalent co-registered secondary bursts. Now we are in the strip map-like stage. All we need to do is cross-multiply. At this point, you could also do ionosphere correction. We are going to skip it because we didn't set up the options for it in the topsApp.xml, but I would encourage students to read up on it and set up these options and run it. But like we said yesterday, you have to run through every step. It will run through it and say you didn't ask for it, so I'm just skipping it. And at each step, it will list the remaining steps left in the workflow for you. So now we have the co-registered bursts. We are ready to generate the interferogram. The interferogram generation happens in these typical steps. Burst IFG. Here we produce the interferogram burst by burst. Then the merge bursts. This is where the spatial mosaicing occurs because all we have is individual interferograms. And then the filtering. This is same as yesterday. If you want to clean up the quality of your interferogram, you want to do some adaptive filtering on it. So these 3 steps together form the interferogram generation step. In this particular data set, we're only looking at a 6-day pair, and we're looking at a fairly arid region. So I suspect you may have completely skipped filtering, but the default is to apply a certain amount of filtering. But that is controllable via the input file. So at the burst IFG step, you will see a fine interferogram folder being created, again organized by SWATs, and you will see each burst's individual interferograms and coherence files, and a multi-looked interferogram. This multi-looking factor is what we supplied in the input file to begin with. This is a full resolution, single look interferogram. So if you were to plot the multi-looked interferogram, here I'm plotting the interferogram for burst 3. This is what the amplitude and the phase looks like. Now you can clearly see the earthquake signal in that particular burst. And you will also notice the 0 padding around the burst in all of these individual burst products. So the next step is, we have these burst by burst interferograms. We put them together. That's what happens in merge steps, merge bursts. And when you look at merge interferogram, you should see all the 4 bursts put together into one single mosaic interferogram. And you'll see there are no more, all the 0 padding and all that has been accounted for in the merging process. So like I said, this is a very nice interferogram to play with because it's been sampled in multiple geometries with multiple temporal baselines, and it's a tiny area, so you can actually afford to process all of them fairly easily. There's a question on chat. If you got an error running that step, you probably skipped a step before. Did it say did not find? Yeah, you have to go in sequence, even though you don't actually intend to do the ionosphere correction in this case. You have to run through the sequence, let the workflow see that you did not ask for it, and then skip it. Any questions so far on the interferogram generation? So the last part of the interferogram generation is the filtering. We use a Goldstein-Werner filter, the default. Here we want to compare the filtered and the unfiltered interferogram. So on the top is the merged unfiltered interferogram, and the bottom is the merged filtered interferogram. The adaptive filtering applied to it. You'll see a lot less speckly noise that Paul pointed out yesterday in his lectures. A lot of that gets cleaned. Phase looks a little cleaner. This cleaning up essentially speeds up phase unwrapping a little bit, which is why it's applied by default. But again, it's controllable via the input XML files. You can control how much filtering. It really boils down, what's the typical strength of the filter, right? I think by default, this one uses the same filter strength as what was in ROIPAC, which is probably 0.7, which is probably a little too heavy. I can, or 0.5. So 0.5 is the typical number people typically use for the Goldstein filter. If you want milder filtering, you go towards 0. If you want heavier filtering, you go towards 1. Filter strength of 0 essentially means no filtering. At present, I think the patch sizes are fixed in ICE2. I don't think we ever play with it. At least, yeah. We haven't seen significant changes, but yes, that's another thing to study. What would be the downside of stronger filtering? So this filtering typically, again, comes in, is only used in like tectonics applications where you're looking at wide area signals. Any sort of high resolution approach typically does not use filtering. Downside of stronger filtering is you lose resolution. You're smoothing your features. But for many tectonic applications, resolution of 500 meters is more than sufficient for modeling. It may not be acceptable for certain other applications. Probably not very suitable for landslides.
It can cause unwrapping errors too, right? By blowing through the boundaries between.
That's correct. Yeah. If you have a sharp discontinuity, it can blow through it. It can eliminate it because you're essentially smoothing the signal. Any questions? Have people gotten this far so far? Anyone? Cool. Yes. So here we have the filtered interferogram. The next step in the process is exactly the strip map processing. We need to unwrap this data. Unwrapping can be done in 2 stages. We're not doing the second stage unwrap I think the discussion about this came up yesterday with islands and so on. The second stage essentially tries to resolve any ambiguities between islands. It's not a foolproof way. It just tries to minimize the number of cycle jumps between the different connected components that it finds. In this case, in our input file, we've already specified the unwrapper to be snafu. So go ahead and push the button on it. This could run for a couple minutes, I think. There are multiple options, ICU, snafu, snafu MCF, then GRASS. ICU was what was used for the SRTM mission. The way it works is it introduces random seeds all over the images and grows, like Paul mentioned yesterday. GRASS is probably the most rudimentary unwrapper. You have to manually specify the seed for unwrapping and grow it, and it only unwraps one connected component. So if it hits a barrier from your seed, that's pretty much the only part of the image you unwrap. Snafu has two variants, Snafu MCF and Snafu as out of the box. Snafu is an iterative algorithm. It first solves a fast problem, then it iterates on the solution. There are multiple ways of generating the first solution. If you leave it up to Snafu by default, it generates the default solution using what is called a minimum spanning tree, and then iterates on it, and it could take very long, like you heard yesterday. What we find is a better first solution is generated with Snafu MCF. The other one's called Snafu MST, but we typically ignore the MST part of it. First solution is generated using minimum cost flow. And if the solution is really good enough to begin with, the iterative part of Snafu has very little to contribute. So in the Snafu MCF, only the first good solution is generated, and we terminate the processing at that point. So once you've run this, you can plot the unwrapped phase as well as the connected components. So the unwrapped phase for this earthquake looks like that, whereas the wrapped phase looked like that. So this has tried to resolve phase cycles, and you see sort of high frequency patterns here in this part of the imagery where my cursor is showing. And if you actually look at the connected components, most of it seems to be one, except you see this little tiny speckle, little small connected components in that area. What Snafu is trying to tell you is I gave you a solution in this area, but it may be off by a few cycles. All pixels within a connected component are consistent, but pixels in one connected component need not be consistent with pixels in another connected component. So the two-stage unwrapper would potentially try to normalize this, but this is what Snafu generates out of the box. I would always say interpret the phase you get in using the connected component as a guide. Unfortunately, I don't know enough about this this particular event to interpret it for you. If someone, the audience or Gareth, wants to talk more about this, I'm happy.
From what I remember about the discussion of it when it occurred, the interferogram is consistent with there being a component of strike slip in one area and a component of normal slip in another. So you'll see it when you process a different viewing geometry. Is this the descending interferogram?
This is the descending one, yes.
Yeah, so if you process the ascending one, you see some of the same features in it, which suggests that those are mostly vertical motion, but then other parts of the pattern are reversed, which suggests horizontal motion. So it's actually quite interesting and a bit more complicated than what we saw this morning, say.
Yep. So the magnitude of the unwrapped phase goes from about 40 radians to about -20 radians. So from peak to peak. And the interesting thing is the connected components go from 1 up to 20. So we're seeing this big chunk of blue, which is 1, but there are tiny islands in it, which are labeled with different connected components in the unwrapped phase. So now that we have the unwrapped interferogram, the last step is to put all the data on a map. So we run the single step. So yesterday, the multiple ways of running single step, you saw minus minus star equals the step name, minus minus end equals step name. You could also just go do minus do step geocode and it'll run a single step for you. So this step basically takes the data that you've just generated and resamples it to the same grid as the DEM you provided it. So we provided it a 30-meter SRTM DEM. The output will be on the same grid as the input DEM. And by default, certain products are geocoded. You can also control which products you want to geocode by controlling the inputs in the XML file. So when you run the geocoded data, now this is in lat long space, and that's what the geocoded data looks like. The geocoding is typically just nearest neighbor. The only different thing is if you're geocoding complex data, it uses a sync interpolator. All other, by default, just use nearest neighbor. Are people able to get this far? I think the geocode step should be reasonably fast, a couple of minutes. I think you did not read the instructions correctly and you just walked through the cells. That is a user exercise. That is for you to change the input XML file, create the XML file. I think the error that you're reporting is a user exercise. So I would say go through this carefully. This is the next step. So in this workflow, we've used the same DEM that we downloaded, but often we want to bring in our own DEM, or we want to use the what's the question? That is correct. Imagery gets stretched as we project into different map projections. I've included a section on how to bring in your own DEM or to change the DEM characteristics for geocoding. I leave this as user exercises. User can play with it. There are some utilities within ICE that will let you do this. And yeah, another exercise is if you want to bring in your own DEM. Typically, what we do for polar stereo with Arctic DEM, you'd have to do these steps. These are the different steps involved in bringing that into the ICE processing workflow. Another thing we can run is pixel offsets. Again, I would say run this. In this case, the deformation is not too big, so I would not be surprised if you don't see a lot, but you should still be able to at least point out where the earthquake happened. The workflow is set up in such a way that you can turn off interferogram generation and just do offset generation, in which case you can directly use this workflow for like ice sheet applications. So there's a lot of bells and whistles to the workflow that you can control with the input XML file. I also tried to put together a set of recommended user exercises for people to get familiar with it. You can process complete Sentinel-1 frames. Like I said, in this case, we restricted the area, not just with the SWAT number, but with the region of interest. You can take both of those out, and by default, it'll process the entire frame for you. You can process multiple Sentinel-1 frames We can't do interferometry with Sentinel-2. Sentinel-1 frames together. Like I said, in the input file for the reference and the secondary dates, XML files, you just make it a list of save files instead of individual save files. Ionosphere is another option you can play with. I would say Ionosphere estimation for Sentinel is a lot more tricky than StripMap. And there are a lot of options that Shunren has added that you may have to control to get the default options seem to work very well in nice arid regions, so it may work out of the box for Nevada. But if you're trying to do this over your area, you may have to fine tune some of the parameters based on your coherence. You can also buy bells and whistles. Yes, it is possible to control dense offset windows again through the topsApp.xml. Bells and whistles for ionospheric filtering steps, again through topsApp.xml. It's a lot of options in topsApp.xml. Yeah. I would also recommend users to get familiar with interferogram post-processing, amount of filtering, amount of what kind of unwrapper might work for their areas. All of these SNAFO MCF seems for us to be sort of a good trade-off across different decorrelation regimes and so on, but none of these options are absolutely perfect. There's always room for fine-tuning them. And one of the questions we often encounter is Esd needed? Depends on who you ask and what your application is. For me, it is yes, it's absolutely needed. But convince yourself by playing. You can turn it on and turn it off. And you can reach a conclusion on that. I've also included some reference for this notebook. Did anybody manage to run the geocoding step and see this? Okay, good. So the size of the data set seems reasonable for the duration of the class. Good. We were worried this was going to take too much time. Any questions?
Just a little secret to make the class work. We actually had to go to the next bigger size, so everybody can use more CPU power than we originally asked for. So.
Yeah, I was suspecting something like that happened, and like that went through quickly.
Yeah.
Is there anything implemented?
There's more machines available at that class?
We don't really know. We basically, I think a few on the class still run the 8x large, other ones run the 16x large, and we sort of spread it out. So there was a lot of fixing on the back end from the team. They all got together and it made this work. So none of them is here, but thank you to the team. And again, I want to apologize. This is really an odd issue that shouldn't happen with a company like AWS, where resources are pretending to be unlimited, but apparently that's not entirely the case.
All worked out. Well done. Thank you.
I think this is by far been the most seamless topsApp run, I think, so far.
Yeah, maybe in the future, if we run the class again, we can have them reserved, pre-reserved some setter. Okay.
Yep. So that's all I had. I think I'm on schedule. It's weird.
Yeah, that's excellent. Thank you. Lots of good questions all the way through. Is there tropospheric correction in ICE? Not directly, but there are other tools that I guess are part of the pre-course and I think will be mentioned tomorrow briefly.
And maybe one issue that some people ran into is we like you know, what Piyush had here, sort of the what do you call it, the collapsible headings where you can organize your code, but it does hide some code cells at times. And I think when you ran into issues where, you know, a code line didn't succeed, it most likely is because you forgot to run an earlier code cell that was not immediately visible to you. So, you know, if you run into an error in the code, then most likely, you know, try to go back and make sure that you have actually run all the cells.
Yeah, I'd also like to say that this is probably, I mean, Paul can correct me, that this is probably going to be a similar app for InSAR whenever InSAR launches. So that generates a pair of interferograms from it. So it's good to get used to the structure.
Absolutely.